Each night, uncountable trillions of stars stare down at you in absolute silence. Researchers have determined that our galaxy alone harbors more planets than all the grains of sand lining every shore on Earth. The mathematics suggest the cosmos should be overflowing with intelligent beings, and yet nothing reaches us. No transmission, no visitor, no indication of any kind. Just a silence so complete it verges on the unthinkable. Tonight, we work through every serious theory scientists have advanced to account for that emptiness. From a galaxy-wide mechanism of annihilation to civilizations hiding in terror, to the breathtaking possibility that we are literally the very first thinking minds in all of existence to pose this question. If this idea keeps you awake at night, hit like and subscribe. Now, prepare yourselves. We are starting. The universe is approximately 13.8 billion years old. Across that staggering expanse of time, stars blazed to life, planets solidified, and the fundamental ingredients of life scattered themselves across hundreds of billions of galaxies. The calculation is not complex. It points decisively toward life having appeared countless times in countless places long before our species took its first steps. And yet every instrument we turn toward the sky delivers the identical answer. Silence. This is the Fermi Paradox, named for physicist Enrico Fermi, who in 1950 posed a question so elemental it continues to disturb the scientific world today. If the universe is this old and this vast, and the chemistry of life seems to arise this readily, then where is everybody? Here is what makes the question genuinely alarming. We are not merely talking about a missing radio message from some distant world. We are talking about the total and complete non-existence of any detectable trace of intelligence anywhere outside our planet. No relic, no megastructure, no engineered transmission. A universe this enormous, this aged, and this chemically abundant should be crowded with conscious minds. Instead, it looks deserted. To fully grasp the weight of that silence, take a moment to consider the scale. Our galaxy alone holds somewhere between 200 billion and 400 billion stars. Astronomers have established that most of those stars are orbited by planets. A considerable fraction of those planets sit inside what scientists call the habitable zone, the band of orbital distances where liquid water can exist on a surface. If even 1 in a million of those planets spawned intelligent life, our galaxy alone would host hundreds of thousands of civilizations, many of them millions of years further along than us. A civilization merely 1 million years more advanced than humanity would have had more than enough time to crisscross every corner of this galaxy many times over, even with technology only marginally beyond what we currently possess. The question is not simply where the aliens are hiding. The deeper question is why nothing has ever reached us. No probe, no message, no engineered object passing silently through our solar system. That absence demands an explanation. Scientists have put forward dozens over the decades. Some are reassuring, most are not. They run the gamut from the possibility that life is far more unusual than we assume, to the terrifying idea that some force systematically prevents civilizations from enduring long enough to make contact. Every proposed explanation carries implications for what our own future might look like. Before we work through those theories, it is worth sitting with the strangeness of the problem itself. Every time our civilization has mounted a search, we have pointed radio telescopes at carefully chosen frequencies, deployed optical instruments searching for laser pulses, and run automated sweeps cataloging unusual stellar behavior. These searches have been constrained, yes, but the silence has been complete. Some investigators argue our search is too narrow, that we are listening for one type of signal in a universe that may communicate through mechanisms we have not yet conceived. That criticism is fair, and it makes the problem thornier, not easier to wave away. What Fermi understood in 1950, and what keeps researchers staring at their ceilings today, is that the silence is not merely strange. It is very nearly mathematically impossible to explain. The universe had every condition necessary to fill itself with minds. Something interfered. Whether that something lies in our past or still waits ahead of us is the question that changes the meaning of everything. Because the next theory we will examine does not simply describe the silence. It proposes that the silence may be the most important warning our civilization has ever been issued. In 1960, astronomer Frank Drake stood at a chalkboard and wrote an equation that was never meant to deliver precise answers. Its purpose was to give structure to our uncertainty. The Drake equation mapped out every variable needed to estimate the number of communicating civilizations currently present in our galaxy. And when you engage with it honestly, it does something unexpected. It identifies exactly the point where confidence dissolves and where something close to dread begins to take its place. The equation multiplies a series of factors in sequence. How many new stars are born in our galaxy each year? Of those, how many have orbiting planets? Among those planets, how many fall within the habitable zone? Of that group, how many actually give birth to life? Of those, how many produce intelligent life? How many of those build a technology capable of reaching across space? And finally, how long does a given civilization survive and broadcast before going quiet? The opening variables are now reasonably pinned down. Decades of astronomical study have established that our galaxy produces roughly 1 to 3 new stars per year. Most of them have planetary systems. A meaningful fraction contain worlds at the right orbital distance for liquid water. These numbers, confirmed by the Kepler Space Telescope and the missions that followed it, suggest hundreds of millions of potentially habitable worlds in our galaxy alone. Then the equation collides with a wall. The instant you arrive at the question of how many of those habitable worlds actually generate life, scientific certainty evaporates completely. We have exactly one verified example of life in the entire universe: Earth. Everything beyond that is speculation layered on speculation. Some astrobiologists maintain that life appears almost inevitably wherever chemistry permits, because the building blocks are so chemically inclined toward self-organization. Others contend that even on Earth, the transition from raw chemistry to a self-sustaining, reproducing cell may have been a near impossibility requiring hundreds of millions of years and a chain of astonishing coincidences. That single, undefined variable swings the final count from millions of civilizations down to exactly one: us. And we have no dependable way yet of knowing which view sits closer to reality. But here is where the equation grows stranger. Even if we accept that life appears with some regularity, there is one more variable embedded in the formula that quietly consumes everything else. The final term is the operational lifespan of a communicating civilization. How long does any species capable of building technology persist before going dark? If civilizations typically survive only a few thousand years after developing radio capability, which is roughly the time frame humanity currently occupies, then the galaxy could be dotted with brief sparks blinking into existence and then out again, never overlapping in time. Two civilizations might each endure for 1,000 years, and yet be separated by a gulf of millions of years. They would never find each other. This is what researchers call the temporal spacing problem. It ranks among the more quietly devastating resolutions to the Fermi Paradox. Not a catastrophic explosion, not a cosmic predator. Just time, immense and indifferent, holding every mind in the universe permanently apart. Drake himself fed numbers into the equation at a conference in 1960 and arrived at a tentative estimate of perhaps 10 communicating civilizations in our galaxy. Current estimates range from below 1 to tens of millions, depending entirely on how generously you assign values to the unknown variables. That spread says everything. We are not close to resolving this. We are standing at the outer boundary of what can presently be known. And one of the most disturbing explanations for why the equation keeps delivering low-number centers on a concept scientists have called the Great Filter. The Great Filter is not a physical place. It is not a coordinate you can locate on any star map. It is an idea first formally presented by economist Robin Hanson in 1998, and it may be the most unsettling concept ever packaged into clean, logical language. The reasoning is straightforward. If intelligent life is genuinely possible, and the universe is ancient enough to have produced it an enormous number of times, but the galaxy looks empty, then something must be destroying or blocking civilizations before they can be detected. Something is standing between life and the stars. The filter might be a single devastating barrier, or a succession of progressively harder hurdles. It might operate at the chemical level, preventing life from ever igniting. It might function at the biological level, blocking the emergence of complex cells. It might act at the cognitive level, preventing animals from developing tool use. Or it might operate at the civilizational level, preventing any species from surviving long enough to reach other star systems. What makes the filter terrifying is not the fact of its existence. It is the question of where it sits relative to our current position. If the Great Filter falls behind us, then humanity is staggeringly lucky. We already cleared the hardest obstacle, whether that was the first appearance of life, the evolution of the complex cell, or the emergence of intelligence. One of those transitions was so improbable that virtually no other lineage in the galaxy made it. We did. The path ahead may actually be open. But if the Great Filter lies ahead of us, the calculation flips entirely. Every civilization that reaches our current stage eventually hits a wall it cannot get past. Nuclear war, ecological breakdown, artificial intelligence that slips beyond meaningful oversight. Some technology not yet invented turning against the minds that built it. In this version of events, the silence of the universe is not a mystery. It is a pattern. Every civilization before us reached this same point and failed. We are arriving at it right now. There is a way to estimate which scenario carries more weight, and the method will make you deeply uneasy. Finding life somewhere else would normally feel like a triumph. But under the logic of the Great Filter, it would be reason for alarm. If we discover microbial organisms on Mars, or complex life in buried oceans beneath some distant moon, or chemical biosignatures in the air of an exoplanet, we learn that the emergence of life is not the filter. Life can get started. That means the filter must sit further along the road, closer to where we are standing, possibly just ahead. every additional world where life is found raises the probability that the catastrophic barrier lies in our future rather than our past. The more abundant life turns out to be, the darker our own prognosis may become. This is not a fringe interpretation. It is an accepted framework in scientific circles. What we can state with confidence is this: the silence is genuine. The mathematics require an explanation. And whatever is doing the filtering has been effective enough to leave an entire galaxy seemingly vacant. The question of whether the great filter lies behind or ahead of humanity is among the most consequential in all of science. Two researchers can examine identical data and arrive at completely opposed conclusions, both internally consistent, one ending in measured hope, the other in something close to despair. The case for the filter lying behind us rests on a chain of biological transitions, each appearing in retrospect almost ludicrously improbable. The first is the origin of life itself. For hundreds of millions of years after Earth's formation, the surface was barren rock. Life did not leap immediately from available chemistry. It required enormous stretches of time and a remarkable accumulation of molecular accidents. The exact mechanism by which the first self-replicating molecule came into being remains incompletely understood. Scientists do not yet have a complete model of abiogenesis, the process through which chemistry becomes biology. But that transition may not even represent the hardest step. Approximately 2 billion years after primitive bacteria appeared, something stranger occurred. One bacterium was taken inside another cell, and instead of being digested became a permanent resident, a built-in energy-producing structure. That merger gave rise to the mitochondria. That event gave rise to the complex cell, the cellular architecture underlying every multicellular organism on Earth. It appears to have happened exactly once in 4 billion years of biological history. Every plant, every animal, every fungus alive today traces its lineage back to that single extraordinary merger. If steps of this kind represent the filter, then we have already survived them, and the path forward holds at least some possibility of being navigated. The case for the filter lying ahead is more difficult to set aside. Look at the behavioral record of the only civilization we can actually observe. Humanity reached radio capability approximately 100 years ago. In that same century, we developed nuclear weapons with the capacity to end civilization, began altering the atmosphere in ways that destabilized the systems supporting our societies, and launched the construction of artificial intelligence systems whose long-term direction no one can reliably forecast. We are a species that accumulates catastrophic capability faster than it accumulates the wisdom to apply it responsibly. If this pattern is not unique to us, then the filter ahead is not a cosmic accident. It is a developmental trap that every species walks toward, and most do not walk out of. There is also a third possibility that few researchers openly explore. The filter may not be a single event at all. It may be a cascade of compounding obstacles, each reducing the surviving population of civilizations until the number capable of reaching interstellar scales rounds to zero. No individual step eliminates everyone, but each step clears the field enough that by the time a civilization could be detected, statistically none remain. We occupy a specific point along this trajectory. Whether the most dangerous hurdles are already behind us, or whether we are approaching the edge of the most lethal threshold any civilization has ever faced, we genuinely do not know. In 1998, paleontologist Peter Ward and astronomer Donald Brownlee advanced a hypothesis that cut sharply against decades of optimistic reasoning about life in the cosmos. Their argument was not that life is impossible elsewhere. It was that complex multicellular intelligent life requires such a precise convergence of conditions that Earth may be genuinely extraordinary. Not just fortunate, but almost impossibly so. The argument opens with location. Earth orbits within what astronomers identify as the galactic habitable zone, far enough from the radiation-saturated core that gamma-ray bursts and supernova shock waves do not repeatedly sterilize it, but not so distant that heavy elements needed to build rocky planets become sparse. Our star is a steady, mid-aged sun that has not dramatically varied its energy output in billions of years. Our oversized moon locks Earth's axial tilt into a stable range. Without that stabilization, our planet's axis would wobble erratically, generating wild climate swings that would almost certainly have prevented stable ecosystems. Jupiter acts as a gravitational shield, pulling in a large share of comets and asteroids that would otherwise bombard Earth with catastrophic frequency. Add plate tectonics that recycle carbon and regulate global temperatures, a magnetic field shielding the surface from lethal radiation, an oxygen atmosphere produced by early photosynthetic organisms, and the narrow thermal window that kept water liquid across billions of years. What emerges is not a typical world. It is a portrait of an extraordinarily fine-tuned system in which an improbable number of independent factors converged in the right configuration at the right time. Ward and Brownlee argued that while simple microbial life might be broadly distributed across the cosmos, the full combination of conditions needed for complex life is so improbable that worlds capable of generating intelligence might number only in the dozens across an entire galaxy, or fewer. The rare Earth argument requires no filter, no catastrophe. It requires only that genuine complexity is extremely hard to generate. If Ward and Brownlee are correct, the silence carries a quiet explanation. Not that civilizations rose and destroyed themselves, but that the preconditions for intelligence were almost never assembled in the first place. In 1973, astronomer John Ball proposed something that sounds almost comforting until you look at it long enough. His idea, known as the zoo hypothesis, holds that intelligent civilizations do exist in the galaxy. Advanced ones, possibly ancient ones, and they know we are here. They simply elect not to make contact. The reasoning echoes what we ourselves do with wildlife reserves or isolated communities. We observe, we document, we do not insert ourselves, not because we are uncaring, but because we understand that uncontrolled contact with a less developed society destroys the very thing you wished to study. An alien civilization, tens of millions of years older than ours, would have sound reasons to stay hidden. Consider what history records every time a technologically dominant society makes contact with a less developed one. The less developed culture is overwhelmed. Its social architecture collapses. Its inherited belief systems shatter. Choosing not to interfere may be the most genuinely ethical response possible to finding a young, fragile mind on a fragile world. Under this hypothesis, the silence is not emptiness. It is deliberate restraint. There may be an entire consortium of elder civilizations that have reached a shared agreement to leave emerging species undisturbed until some threshold is crossed. The zoo hypothesis is by nature almost impossible to evaluate. If a civilization has the sophistication to hide completely from our instruments, we would have no mechanism for detecting it. Some researchers push this into darker territory. not a nature reserve maintained out of compassion, but a quarantine maintained out of caution. A civilization that has watched younger species destabilize their regions of space might isolate developing worlds not for the newcomer's benefit, but for the safety of everyone already established. In that reading, the silence is not a gift. It is a perimeter. What the zoo hypothesis implies, unsettlingly or not, is that advanced civilizations survive long enough to accumulate genuine wisdom. The next theory assumes something entirely different. The dark forest theory arises from a thought experiment so bleak it is genuinely difficult to hold in the mind. Popularized by Chinese science fiction author Liu Cixin, its underlying logic is not literary device. It is a game-theoretic argument about survival in a cosmos where resources are finite and intentions can never be verified. The theory rests on two premises. First, the primary imperative of every civilization is its own survival. Second, the universe does not contain enough resources for unlimited growth by unlimited civilizations. From these two premises, an extraordinarily grim conclusion follows. Imagine you are a civilization that has just detected a signal from another intelligent species. You know nothing about them except that they exist and can broadcast. You cannot confirm whether they are peaceful or aggressive. If they are peaceful and you make contact, you gain an ally. If they are hostile and you make contact, you have told a potential predator exactly where you are. If they are peaceful and you destroy them preemptively, you lose one partner. If they are hostile and you destroy them preemptively, you survive. Under conditions of resource scarcity and the impossibility of verifying intentions across interstellar space, the rational strategy collapses to one answer. Strike first without exception. Under the dark forest model, the galaxy is not quiet because life is rare or civilizations are unstable. It is quiet because every civilization that survives long enough to grasp this logic goes completely silent. Announcing your presence is not an act of openness. It is a targeting beacon. Every star is a potential threat. Every civilization is a creature slipping through the dark, making no sound, leaving no trace, hoping nothing notices it. The implications for our own situation are disturbing. Humanity has been broadcasting electromagnetic signals for more than a century. Those transmissions have already reached more than 100 light-years into space, washing across thousands of stellar systems. If the dark forest model is accurate, we may have already committed the worst possible error. Stephen Hawking publicly warned against deliberate transmissions before his death. The theory's most significant vulnerability is the assumption that cooperation is never worth attempting. But that argument depends on the assumption that wisdom and technological power scale together. The historical record offers modest support for that view. Every civilization in the human record has eventually ended. Empires, cultures, city-states, languages, species. The arc of emergence, dominance, and collapse is so consistent that it barely draws attention anymore. But when mapped onto the Fermi Paradox, it stops being background noise and becomes the loudest possible signal. The self-destruction hypothesis holds that intelligent civilizations routinely eliminate themselves before achieving meaningful contact with others. Not through cosmic calamities, not through alien adversaries, but through their own technologies and their own decisions. In the roughly 250,000 years that anatomically modern humans have inhabited this planet, virtually all of it was spent in small scattered communities with minimal planetary impact. Then, in the last 12,000 years, We built agriculture, cities, and organized states. In the last few centuries, we industrialized. In the last 100 years, we split the atom, began altering the atmosphere, and started building artificial intelligence systems that no individual fully understands or controls. With every passing century, humanity's capacity for accidental or deliberate catastrophe grows faster than our ability to govern it. Nuclear arsenals exist today that could end complex life on this planet. Engineered diseases are becoming progressively more accessible as biotechnology matures. Climate change is already disrupting the conditions supporting our civilization, and artificial intelligence is advancing along trajectories that its own designers describe as potentially ungovernable. These are not hypothetical scenarios. They are confirmed, documented, present-day realities. The self-destruction hypothesis poses a precise question. If this pattern of capability outpacing wisdom is universal among intelligent species, how many civilizations navigate the passage from a planetary-scale species to an interstellar one? If the answer approaches zero, the galaxy fills with brief, vivid civilizations that burn themselves to nothing before launching a single probe beyond their home star. Researchers sometimes call this interval the critical phase. On Earth, that window opened approximately in the middle of the 20th century. It shows no sign of closing. What makes this especially resonant is the arithmetic. Even if 99 out of every 100 civilizations navigate the critical phase successfully, the galaxy would still contain thousands of surviving civilizations. The silence would remain inexplicable. For this hypothesis to fully account for the emptiness, the survival rate would need to be vanishingly close to zero. We are not studying a past civilization that failed. We are the civilization that has not yet determined its outcome. The berserker hypothesis is not a literary metaphor. It is a precise logical argument about what a sufficiently advanced civilization might do to secure its own survival indefinitely. The concept entered public awareness through science fiction by Fred Saberhagen, but its premise has been seriously evaluated by researchers in astrobiology and existential risk. The hypothesis proposes that at some moment in galactic history, one or more civilizations engineered self-replicating autonomous probes with a single directive: find and neutralize any other civilization before it can become a rival. A civilization that endures for tens of millions of years eventually confronts a specific problem. Any other civilization permitted to develop will eventually reach comparable capability. The strategically clean solution is to eliminate competitors while they are still incapable of resisting. The self-replicating mechanism solves the problem of scale. No armada is required. A single probe capable of harvesting raw materials from asteroid belts, fabricating copies of itself, and dispersing can, over millions of years, multiply from 1 into trillions, spreading methodically across the galaxy. Any planet exhibiting signs of technological emergence gets identified and acted upon. Under this model, the emptiness of the universe has a clean explanation. We have simply not been found yet, or perhaps we have, and the countdown has already begun. There is no confirmed evidence of berserker probes, no detected artifacts. But if the probes are built to be undetectable, we would not recognize them. If they are engineered for patience, they might hold position until a civilization reaches some specific developmental threshold before acting. We would receive no warning. Some researchers have noted that Oumuamua, the anomalous interstellar object that passed through our solar system in 2017, could in principle fit the profile of an artificial probe. This is not the scientific consensus, which leans toward a natural explanation, but the object's behavior did not neatly match any established natural model. What gives the berserker concept its staying power is the internal coherence of the logic. In a universe where competition for survival is real and technological capability grows without a natural ceiling, preemptive elimination is a defensible long-term strategy. It is disturbing precisely because it is rational. In 2020, a team of researchers including Robin Hanson proposed a model that reframes the Fermi Paradox in a way that dissolves much of the accumulated speculation. Their framework, the Grabby Aliens model, begins from a single premise. Once civilizations reach sufficient technological capability, they expand outward rapidly and do not stop. The model does not posit hostility. It simply holds that a technologically mature civilization, given sufficient time, will spread through space at a meaningful fraction of the speed of light, colonizing star systems and leaving behind a visible, expanding edge of inhabited space. The core insight is about timing. If civilizations of this kind had existed and begun expanding even 1 billion years ago, their expanding boundaries would already have reached us. The galaxy is old enough, and the physics of expansion at even a modest fraction of light speed is efficient enough, that any civilization with a meaningful head start would have made physical contact by now. The fact that no such civilization has contacted us is itself highly significant data. The model interprets this in one of two ways. Either no such civilizations have developed because something stops them from reaching the expansion threshold, or they exist but have not yet launched, meaning we are living very close, in cosmic terms, to the moment the first wave of expanding civilizations will emerge, and we ourselves might be among them. If galaxy-spanning, civilizations are rare but inevitable, and if we are close in cosmic time to when the first ones appear, then humanity may be among the earliest species ever to approach this boundary. We are not latecomers to a long-running event. We are early by an enormous margin. The universe looks empty right now because the age of expansion has not yet started. What we are living through may be the final silence before an extraordinarily loud era begins. The simulation argument was formally presented by philosopher Nick Bostrom in 2003. It does not claim that we live in a simulation. It lays out a trilemma. One of 3 propositions must be true. Either nearly every civilization at our stage collapses before acquiring the capacity to run detailed simulations of conscious minds, or nearly every civilization that reaches that capacity chooses not to run such simulations, or we are almost certainly inhabitants of a simulation right now. The logic runs as follows. If even a single civilization in the history of the cosmos survived long enough and decided to operate detailed simulations of conscious experience, it could generate a virtually unlimited number of such minds. The simulated minds would outnumber the original minds by an astronomical ratio. Therefore, any randomly selected mind, including yours, is statistically far more likely to be one of the simulated ones. Now connect this to the Fermi Paradox. If we are embedded in a simulation, the emptiness of the observable universe requires no explanation. The sky is vacant because whoever is running the simulation chose not to populate it. No other civilizations transmit because none were rendered with sufficient fidelity to transmit. The universe extends precisely as far as its observers need it to. Beyond the range of our instruments, there may be literally nothing. Not empty space, but the absence of rendered code. From the perspective of the Fermi Paradox, the simulation resolution is simultaneously the most economical and the most structurally destabilizing. It requires no great filter, no self-destruction, no alien predators. What makes this theory resonate is its explanatory brevity. The silence is not a problem requiring a solution. It is a creative decision. And if it is a creative decision, the question shifts entirely. Not where is everyone, but why were we authored to feel alone? For most of the 20th century, astrobiology operated on a quiet assumption that life, once it begins, follows a general trajectory toward increasing complexity over time. Microbes give rise to multicellular organisms. Multicellular organisms develop nervous systems. Nervous systems produce brains. Over the past 2 decades, that assumption has been systematically dismantled through a growing accumulation of detail about just how arbitrary and fragile the path from microbial to complex actually was on our own planet. Life appeared on Earth within a few 100 million years of the planet's surface cooling. That is relatively fast in geological terms. But then, single-celled organisms dominated the planet for roughly 3 billion years. 3 billion years of chemistry, natural selection, and environmental pressure, and the structural complexity of life advanced essentially nowhere. Then the eukaryotic cell appeared. This cell architecture underlies every complex organism alive today. It arose from a single symbiotic event in which one organism was absorbed by another and became a permanent, cooperative internal structure rather than being digested. Scientists believe this occurred exactly once in 4 billion years of Earth's biological history. Following the eukaryote's emergence, another billion years passed before multicellular life became widespread. Then came the Cambrian explosion, the remarkably rapid emergence of most major animal body plans, probably triggered by atmospheric oxygen crossing a critical threshold. Each of these transitions required a precise precondition. Miss any single one, and the biological progression stalls. You end up with a planet locked permanently at the microbial level. Researcher Andrew Knoll of Harvard has spent decades studying early Earth life and consistently argues that the emergence of biological complexity was neither a guaranteed outcome nor a predictable progression. It was a stack of contingent accidents, each one dependent on the one before. If this analysis holds, the universe is almost certainly not lifeless. It is probably filled with bacteria, simple organisms flourishing in liquid oceans beneath ice shells and in warm, mineral-rich formations within the crust of countless worlds. But the leap to genuine complexity, to nervous systems, to cognition, to language and technology, may have happened only a small number of times across the entire observable universe. The silence of the sky does not mean the universe is dead. It may mean that complexity is a nearly impossible chain of accidents that completed itself here, and almost nowhere else. There is a version of the Fermi resolution requiring no catastrophe, no filter, no hostile alien presence, and no simulated universe. It asks only for a careful reading of probability alongside the known age and structure of the cosmos. And its conclusion is this: we may be the very first intelligent civilization ever to exist anywhere. This is not an argument from arrogance, it is an argument from timing. The universe is 13.8 billion years old. For approximately the first 9 billion of those years, the conditions required for complex rocky worlds like ours had not yet been assembled. The earliest generations of stars contained almost no heavy elements. They burned brilliantly and collapsed quickly, dispersing carbon, oxygen, iron, and everything else needed for chemistry and biology into the interstellar medium. Only after multiple cycles of stellar birth, death, and enrichment did those elements accumulate in quantities sufficient to build a world like Earth. Our planet coalesced approximately 4 billion years ago. Complex life required more than 3 billion years to emerge. Technological intelligence required hundreds of millions of years beyond that. When you locate humanity within the timeline of cosmic chemical enrichment, we appear at very nearly the earliest moment that beings like us could have arisen. Not millions of years late to a gathering already in progress, but right at the opening edge of the possible. Under this framing, the universe is not yet mature enough to be filled with intelligence. We are not the survivors of a culling. We are not overlooked by an older civilization. We are simply early, among the very first arrivals in a cosmos just beginning to reach the conditions where arrival becomes possible. If we are first, then everything following from us is a blank page. There is no predecessor civilization to learn from, no inherited template, no cautionary record from species that already made the catastrophic mistakes. We write the first entries in what may one day be a cosmos populated with minds, but only if we survive long enough to pass something forward. Researchers such as David Kipping at Columbia University have published work suggesting that the distribution of intelligence emergence times across cosmic history may genuinely favor very early emergence for the first civilization. The solitude this hypothesis describes is unlike the solitude in any other Fermi resolution. It is not the solitude of the last survivor. It is the solitude of the first arrival. The search for extraterrestrial intelligence has been anchored for decades to a single methodology. Radio telescopes pointed at carefully selected frequencies, listening for structured signals that no natural process would produce. This approach began formally in 1960 with Project Ozma and has continued in various forms ever since. It is rational. It is scientifically defensible. And it may be missing the target entirely. Radio waves spread as they travel outward. By the time a signal has traveled a few hundred light years, it has diluted to levels extraordinarily difficult to separate from background noise. Our own most powerful intentional transmission, the Arecibo message sent in 1974, would be essentially undetectable by current human technology, at even a modest fraction of the distance to the nearest star systems. This means that even if hundreds of civilizations were broadcasting simultaneously with technology equivalent to ours, we would be extremely unlikely to detect any of them. Radio is not an efficient medium for interstellar communication at our current developmental level, and civilizations substantially more advanced may have moved on from it long ago. Our own technology has already begun shifting away from high-power, broadly dispersed transmission toward tightly focused, encrypted digital channels. As a civilization's communication network matures, it tends to grow quieter and less detectable from the outside. A highly advanced civilization might be completely invisible to radio-based searches, not because it has gone quiet, but because it has evolved into communication modes we have not yet developed. Tightly focused laser pulses, neutrino-based transmissions, or gravitational wave modulation would all pass through our current instruments entirely unrecognized. What researchers are increasingly calling for is a transition toward technosignatures, detectable indicators of technology that persist at large scales without requiring a civilization to actively broadcast. Waste heat from industrialized worlds detectable in the infrared. atmospheric chemistry inconsistent with any known abiotic process, structured modulation in a star's light curve suggesting engineered objects in orbit. The reasoning is straightforward. If you want to find a city from altitude, you do not listen for phone calls. You look for lights in the dark. Our current search strategy is the equivalent of listening for phone calls from an ocean away, while the civilization we are trying to find stopped using phones generations ago. If a civilization advanced enough to construct structures visible across the galaxy existed, it would announce itself by transforming its environment on so enormous a scale that the evidence would be encoded in the light of distant stars. This is the foundation of technosignature research. And the prime theoretical subject of that search is the Dyson sphere. Freeman Dyson proposed in 1960 that any civilization facing energy constraints would eventually turn its attention to the total output of its parent star. A sufficiently advanced civilization would build a structure, perhaps a distributed constellation of orbital collectors and habitats, that captures a substantial portion of its star's radiated energy. Observed from the outside, a star wrapped in a Dyson swarm would emit less visible light than its mass would predict, while radiating elevated levels of infrared energy. That specific signature is something our instruments are capable of detecting across thousands of light years. Astronomers have produced lists of candidate stars. None have been confirmed as artificial, but the survey effort has only recently become systematic. The Gaia mission, the Wide-Field Infrared Survey Explorer, and future instruments like the Nancy Grace Roman Space Telescope are compiling stellar catalogs at a scale that makes targeted technosignature searches genuinely viable for the first time. Researchers are now applying machine learning to identify stars whose behavior is inconsistent with established natural models. Beyond Dyson spheres, researchers are examining other potential engineering signatures. Stars shedding mass in non-standard patterns might host planetary-scale mining operations. Planetary systems with anomalous orbital architectures might have been deliberately rearranged. NASA formally began funding technosignature research in 2019, a significant institutional shift. One category of technosignature has attracted exceptional attention: starlight that dims in irregular, non-repeating patterns. Not the clean periodic signals produced by a transiting planet, but complex variations in brightness differing in depth, duration, and profile from one event to the next. This behavior has been observed around a real star, approximately 1,500 light-years from Earth. Its behavior has generated more published papers, more competing hypotheses, and more genuine scientific controversy than almost any other individual object in the past decade. On August 15, 1977, a radio telescope at Ohio State University captured something anomalous. The instrument was part of a program called Big Ear, one of the earliest organized efforts to scan the sky for artificial signals. A volunteer named Jerry Amon was reviewing printouts days after the observation when he encountered a sequence of characters bearing no resemblance to anything surrounding it. The signal lasted exactly 72 seconds, the maximum time any fixed point in the sky could remain within the telescope's observation window. It appeared to come from the direction of the constellation Sagittarius. It had the intensity, the frequency, and the narrowband structure that researchers had theorized an artificial extraterrestrial signal would possess. Amon drew a circle around the data and wrote a single word beside it. Wow, the signal has never appeared again. Dozens of follow-up observations have targeted the same region of sky using successively more capable instruments across nearly 5 decades. Nothing has returned. No repetition, no residual echo, no confirming detection from any other telescope. Whatever generated it either passed once and kept moving or simply stopped. This is confirmed observational data. The signal was real. Its characteristics are genuinely anomalous. What produced it remains completely unknown. A comet releasing. Hydrogen gas at a specific orientation was among the more recent candidates, advanced by astronomer Antonio Paris in 2017. Multiple independent teams concluded that the comets in question would not have been in the correct position to produce the observed signal, and that the hydrogen gas mechanism did not adequately account for its narrowband structure. The WOW signal occupies a rare and uncomfortable position, an anomaly with no confirmed natural cause, but equally no confirmed artificial one. What makes it particularly striking is the frequency at which it arrived. The signal appeared near 1,420 MHz, the emission frequency of neutral hydrogen, the most abundant element in the universe. Decades before the detection, researchers had proposed that this frequency would be the natural universal landmark any civilization capable of studying the cosmos would recognize and use for interstellar signaling. The WOW signal arrived precisely there. Nearly 5 decades of follow-up have not produced a satisfactory natural explanation. One detection, one handwritten annotation, nearly half a century of silence from the same patch of sky. In 2015, a paper by astronomer Tabitha Boyajian and a team of collaborators described a star roughly 1,400 light-years away behaving in ways no available natural model could cleanly account for. The star, previously catalogued as KIC 8462852, and now known as Boyajian's star, was dimming. Not in the regular repeating pattern produced by an orbiting planet, not in the smooth, predictable curve of a binary stellar companion. It was dimming in complex, irregular episodes, sometimes by as much as 22% over the course of days, then recovering, then dimming again in an entirely different configuration. 22% is an enormous dimming event. A Jupiter-sized planet blocks roughly 1% of stellar light. Whatever was obscuring Boyajian's star was, by natural standards, impossibly massive, and its transits were not periodic, not symmetric, and not consistent with any established category of naturally orbiting body. The data originated from the Kepler Space Telescope, which monitored over 150,000 stars continuously for planetary transits. Over 4 years of observation, Boyajian's star produced the most anomalous light curve in the entire dataset. Citizen scientists with the Planet Hunters project flagged it as something they had never previously encountered. The irregular dimming profile is precisely what you might expect from a Dyson swarm. A population of large orbiting structures at various stages of construction, each blocking varying amounts of starlight at different times. This appeared in peer-reviewed journals and was taken seriously by credentialed researchers. The scientific community did not ultimately adopt that interpretation. The most broadly accepted hypothesis holds that a cloud of fragmenting dust and debris accounts for the irregular dimming. But this explanation carries its own, unresolved complications. The scale and architecture of the dimming events remain difficult to account for fully. More recently, astronomers established that Boyajian's star is also undergoing a long-term gradual decline in total brightness spanning years, entirely distinct from the acute transit events. Boyajian herself has consistently acknowledged that the object remains incompletely explained. What makes Boyajian's star significant in the Fermi context is what it reveals methodologically. For the first time, astronomers encountered a real stellar system whose behavior a techno-signature researcher would have legitimately flagged as a candidate worth serious investigation. The instruments performed correctly. The anomaly was genuine. The natural explanation remained incomplete. In 2007, astronomers reviewing archival data from the Parkes radio telescope in Australia found a signal that should not have been there. A burst of radio energy lasting only a few milliseconds, but with an intensity so extraordinary it could only have originated from beyond our galaxy. Since that first detection, astronomers have cataloged hundreds of fast radio bursts. Brief flashes of radio energy lasting anywhere from a fraction of a millisecond to several seconds. Each releases more energy in that instant than our sun emits over the course of days. They arrive from across the sky in random directions, indicating sources distributed throughout the universe. For years, their precise physical origin remained entirely unidentified. Most fast radio bursts appeared once and were never seen again. Then, researchers identified a small category that repeated, sometimes on irregular schedules, sometimes in structured cycles. One source cataloged as FRB 121102 was observed repeating in clusters that arrived periodically, then fell quiet, then clustered again. The period of that cycle is approximately 157 days. The leading scientific explanation today centers on magnetars, neutron stars with extreme magnetic fields that rank among the most energetically violent environments known to physics. In 2020, astronomers detected a fast radio burst from a magnetar inside our own galaxy, the first time such an event could be traced to a confirmed source. This established that magnetars can produce at least some fast radio bursts, but it did not resolve every open question. The energy output of certain observed bursts exceeds what current magnetar models predict under standard physics. Some researchers have explored whether a subset of fast radio bursts might constitute technosignatures. Astrophysicist Avi Loeb of Harvard has proposed that a sufficiently powerful artificial emitter designed to propel spacecraft across interstellar distances could generate a fast radio burst as a secondary emission, a model he calls the lighthouse hypothesis. This is not the scientific mainstream, but it has not been ruled out. What fast radio bursts confirm is that the universe contains physical processes generating intense, structured energetic emissions at timescales and power levels we are only beginning to characterize. Every time we have opened a new observational window onto the cosmos, we have found things we did not anticipate. What else remains currently invisible? On October 19, 2017, an astronomer at the Haleakala Observatory in Hawaii detected a rapidly moving object crossing our solar system. Further analysis stopped the field cold. The object had originated from outside the solar system entirely. It was the first confirmed interstellar visitor ever identified, named Oumuamua, a Hawaiian term meaning roughly a scout from the distant past arriving ahead of its message. Initially, astronomers expected a routine classification: an interstellar rock or icy body ejected from some distant stellar system and drifting through space for millions of years. The universe is ancient. Ejected material should be abundant. A passing piece of debris seemed scientifically workable. Then the data came in, and workable became insufficient. Oumuamua's shape had no precedent among any natural objects previously catalogued. Estimates based on brightness variations and reflectivity suggested it was dramatically elongated, with a length-to-width ratio of perhaps 10:1 or greater. No known process of natural formation reliably produces objects with that geometry at that scale. Then came the trajectory anomaly. As Oumuamua moved away from our sun, it accelerated beyond what gravitational forces alone could account for. Astronomers searched for evidence of outgassing. They found nothing. No gas envelope, no dust tail, no coma of any kind. Just an unexplained clean acceleration. Every proposed natural explanation was published and subsequently challenged. One hypothesis proposed it was made of hydrogen ice that would outgas invisibly. The problem: hydrogen ice cannot survive in the interstellar environment long enough to account for its implied journey. Another proposed it was a thin, flat sheet of rock pushed by solar radiation pressure like a natural sail. The problem: an object thin enough to be accelerated that way would need to be at most a millimeter thick across a surface hundreds of meters wide, a geometry for which no known formation process exists. Avi Loeb argued that the most economical explanation for Oumuamua's properties, considered together, was that it was artificial. Not certainly artificial, but that the accumulation of anomalies warranted serious investigation rather than reflexive dismissal. The scientific mainstream continued searching for natural explanations. In 2023, a team proposed that nitrogen ice fragments from a shattered exoplanet could theoretically reproduce the observed properties. This hypothesis attracted attention, but has not achieved general acceptance. A second interstellar object, Borisov, was detected in 2019 and behaved entirely as a comet would. The contrast only deepened the strangeness surrounding the first. Whatever Oumuamua was, it passed through, and the questions it left behind remain open. One of the quieter responses to the Fermi Paradox requires no rare life, no self-destructing civilizations, and no concealment. It requires only that the cosmos is physically structured in ways that make crossing it fundamentally impractical for any civilization, regardless of how advanced. The first barrier is energy. Accelerating a spacecraft to even 1/10 of the speed of light demands an energy expenditure that vastly exceeds anything our civilization currently produces. For a vehicle of modest mass, the energy required approaches the equivalent output of thousands of nuclear detonations. The propellant problem compounds this. Every rocket-based propulsion system must carry its own fuel, but fuel has mass, and greater mass demands more fuel. The relationship is exponential. Chemical propulsion is entirely inadequate. Nuclear propulsion is an improvement, but does not resolve the fundamental problem. Even under the most optimistic fusion scenarios, a rudimentary interstellar mission represents centuries of progress beyond our current capabilities. The second barrier is time. Even at 1/10 of the speed of light, the journey to Proxima Centauri takes roughly 40 years. For a civilization attempting to explore a galaxy 200,000 light-years across, the timescales involved are nearly impossible to internalize. Civilizations waiting for probes to return would need institutional continuity across timescales that exceed the entire recorded history of human civilization multiplied by thousands. The third barrier is collision hazard. Dust particles and microscopic debris become lethal at relativistic speeds. A particle no larger than a sand grain encountered at a significant fraction of the speed of light carries kinetic energy equivalent to a small explosive device. Shielding a vessel against such impacts across decades-long journeys has no current answer. These barriers are grounded in confirmed physics. They imply that even civilizations far more advanced than ours may have concluded that physical interstellar travel is not viable at any scale. The galaxy may be inhabited by intelligent species that have never left their home stellar systems, not from lack of curiosity, but because the underlying physics simply does not accommodate the ambition. In that case, the silence is not evidence of absence. It is evidence of confinement. Most framings of the Fermi Paradox treat it as a spatial question. Where are they? Why have they not come here? But there is an equally powerful version of the same problem that is purely temporal. If the emergence of intelligence is even moderately probable given the right conditions, and if those conditions existed elsewhere in the galaxy several billion years before they existed on Earth, then there may have been civilizations whose entire arc of rise, flourishing, and extinction concluded billions of years before a single hominid ancestor stood upright. A civilization that reached its peak 2 billion years ago would leave no detectable radio signals today. Its transmissions passed through when the most complex life on Earth was single-celled organisms incapable of instruments or awareness. Any physical objects they launched into space would by now be indistinguishable from natural debris. The reverse is equally valid. Civilizations arising in the future will emerge long after we are gone. From their vantage point, we will be the ancient and silent ones. Our broadcasts will have faded to nothing. Two civilizations may share the same galaxy, and yet be so separated in time that the opportunity for mutual detection never exists. The overlap required is not just proximity in space, it is proximity in time. And on cosmic scales, that window is far narrower. Astronomer Milan Cirkovic has written extensively on this, arguing that our search is built on an unstated assumption that other civilizations exist contemporaneously with us. If civilizations endure for millions or billions of years, the peak period of intelligence in this galaxy may already lie mostly in its past. We may be scanning the sky for something that flourished and went quiet long before our instruments existed. Or, if intelligence is genuinely rare and we are among the earliest minds to emerge, then the full abundance of conscious life in this universe may lie hundreds of millions of years ahead of us. We are not late arrivals to a sparse party. We are among the first guests, and the event itself has barely started. There is an assumption so deeply embedded in the search for extraterrestrial intelligence that it almost never gets examined directly. The assumption is that intelligence leads inevitably toward technology. Earth's history seems to confirm this, but Earth's history represents a sample size of 1. Dolphins exhibit self-recognition, intricate social architectures, and problem-solving, abilities that would have seemed remarkable to earlier generations of researchers. Elephants mourn their dead and carry multi-generational social memory. Crows and ravens fabricate tools, anticipate future needs, and track individual human faces across years. Octopuses demonstrate complex learning that evolved in complete biological independence from vertebrate intelligence. None of these species are building radio transmitters. Intelligence and technological civilization are distinct phenomena. Technological civilization requires hands capable of fine manipulation, social structures enabling cumulative knowledge transmission, sufficient environmental pressure to reward innovation, and a metabolism supporting long-term investment in tools. Remove any single one from the picture, and you can produce a world populated with genuinely intelligent beings, leaving essentially no detectable signature from orbit. A world covered by deep oceans could support vast populations of intelligent marine organisms with no access to fire, no capacity to work metals, and no pathway to electronics. From space, their world would look like a featureless ball of water. If even a significant fraction of worlds bearing intelligent life contain species that never develop recognizable technology, the silence of the cosmos resolves without requiring any filter, catastrophe, or concealment. The universe may be populated with minds we simply cannot perceive, because we are looking exclusively for the particular technological signatures our own evolutionary path generated. We are not actually searching for intelligence. We are searching for industrial civilization, and there is no guarantee that intelligence and industrialization are universal companions across all possible biospheres. In the last decade, the inventory of potentially habitable worlds within our own solar system expanded dramatically through the discovery of worlds harboring liquid water locked beneath thick layers of ice. Europa, one of Jupiter's moons, is estimated to hold twice the total volume of liquid water found across all of Earth's oceans combined. That water lies beneath an ice shell potentially tens of kilometers thick, kept liquid not by sunlight but by tidal heating, generated by Jupiter's gravitational pull. The seafloor may support hydrothermal vents where chemical gradients sustain entire ecosystems in complete darkness. Life around Earth's hydrothermal vents exists in total independence from sunlight. This has been confirmed. Enceladus, a moon of Saturn, actively ejects plumes of water vapor and ice crystals from its southern polar region. Analysis by the Cassini spacecraft found molecular hydrogen, silica, and organic compounds within those plumes, chemical signatures of hydrothermal activity, and the molecular building blocks of biology. Titan presents yet another kind of liquid environment. Deep lakes of liquid hydrocarbons raise the possibility of chemistry-based life operating on entirely different principles than water-based biology. A civilization that evolved inside a sealed subsurface ocean beneath kilometers of solid ice faces an almost insurmountable barrier to any form of space-based communication. It would have no access to the electromagnetic sky, no stars, no radio frequencies, no direct line of sight to anything outside its world. Even if such a civilization developed language, culture, and sophisticated technology adapted to its environment, the road to radio transmission and space exploration would first require it to conceive that a universe existed above its ice ceiling. Then find a way to breach kilometers of solid ice, and then survive exposure to a vacuum for which its biology had provided zero preparation. A civilization that has never seen a star does not naturally arrive at the idea of broadcasting into space. Thousands of subsurface ocean worlds may exist across the galaxy right now. Some may harbor complex life, locked in silence beneath their shells, not silent by any choice, but silent by the architecture of their world. When we search for extraterrestrial intelligence, we are searching for something sufficiently similar to our own intelligence that we can recognize it. Structured mathematical sequences, stable frequency patterns, artifacts displaying geometric regularity. But that assumption has never been tested against anything other than the one kind of intelligence we know firsthand. We search for prime number sequences because we would encode prime numbers. We flag anomalous geometric structures because we build geometric structures. Consider what a genuinely alien intelligence might actually be. Not something that shares our evolutionary heritage, our sensory architecture, or our experience of time. Something that arose under radically different selective pressures on a radically different world. Perhaps with multiple simultaneous processing streams, rather than a single continuous thread of consciousness. Perhaps with memory and information distributed across a biological network, nothing like a centralized nervous system. There is no guarantee such a mind would produce anything our instruments would classify as structured communication. Its physical works might appear as natural background noise. Its transmissions might carry information across physical dimensions we do not monitor. We could observe the evidence directly and register nothing at all, not because nothing was present, but because we lack the framework required to interpret it. Researchers in animal cognition have encountered small versions of this problem on Earth. Prairie dog vocalizations encode specific information about the characteristics of approaching predators in ways researchers spent decades missing. Whale song carries structural features sharing mathematical properties with human language. Bee dances communicate precise information about distance and direction through a physical medium no human sensory system can directly access. These are creatures sharing billions of years of evolutionary history with us. An alien intelligence sharing none of that history might differ so fundamentally that the gap between us is not a translation problem, but a categorical one. The Fermi Paradox may not even be asking the right question. The question is not, where is everyone? It may be whether we could identify everyone even if they were somehow present and active all around us. In 1973, molecular biologist Francis Crick, who shared the Nobel Prize for co-discovering the structure of DNA, published a scientific paper with astronomer Leslie Orgel, proposing something the scientific mainstream received with considerable discomfort. Their hypothesis, directed panspermia, proposed that life on Earth did not arise through independent natural chemistry. It was deliberately seeded by an extraterrestrial civilization. Crick reached this conclusion through molecular biology. He was troubled by the extreme improbability of life assembling itself spontaneously within the time window Earth's geological record implied. Life appeared surprisingly quickly after the planet's surface stabilized. The genetic code is also strikingly universal. A single information encoding system shared by every form of life on Earth, from bacteria to redwood trees to human beings. Crick found that universality suspicious. Directed panspermia proposes that a civilization facing the eventual death of its star might have seeded many worlds across the galaxy with microbial organisms or chemical precursors to life. Not to colonize, not to establish communication, but simply to propagate biology as broadly as possible, ensuring that wherever conditions eventually became suitable, life would have a starting point. If this hypothesis is correct, it substantially reframes the Fermi Paradox. The origin of life on Earth might not be an independent data point at all. It might be evidence of a prior civilization that no longer exists. The silence we observe might be the silence of a forerunner, a civilization that flourished billions of years ago, seeded what it could, and then faded into deep time. Recent research supports the physical plausibility of at least the natural version of this idea. Rocks ejected from planetary systems during formation can cross interstellar distances over millions of years and eventually land on other worlds. If those rocks carry dormant microbial life, biology could propagate between stellar systems without any intelligent agent's involvement. Directed panspermia simply adds intention to a mechanism that may function naturally. The precise mechanism by which chemistry became self-replicating biology on Earth remains, as of today, an open scientific question. Crick's hypothesis sits precisely at that opening. In 2001, philosopher Stephen Webb described the planetarium hypothesis. The idea is not that we inhabit a fully computational universe. It is that the universe, visible to us, has been deliberately constructed to appear devoid of intelligent life. A cosmic theatrical set designed to isolate us from the actual reality of what the universe contains. Every piece of information we possess about the universe beyond our solar system arrives through electromagnetic radiation. Every distant star, every galaxy, every cosmic structure we have ever mapped is known to us exclusively through signals that have traveled to reach our instruments. We have never physically visited anything beyond the most immediate edges of our own cosmic neighborhood. A civilization wishing to construct a false impression of an empty universe would not need to alter the actual universe. It would need only to manage the information flowing into our solar system. If such a civilization could intercept or replace the electromagnetic signals arriving at Earth, substituting the signatures of inhabited worlds and alien megastructures with empty noise or naturally appearing backgrounds, we would have absolutely no way of knowing. The planetarium hypothesis cannot be tested with any instrument currently available. An illusion engineered by a sufficiently advanced civilization to be perfectly undetectable would be, by definition, undetectable to us. Every observation we make could fall within the managed domain. This places the planetarium hypothesis at the boundary between scientific epistemology and philosophy. If our inputs are controlled, our conclusions carry no reliable meaning. What the hypothesis shares with other advanced civilization responses to Fermi is the implication that the silence is intentional, not a product of rarity, destruction, or distance, but of active management. The universe appears empty because something has arranged for it to appear that way. There is also a simpler version requiring no active deception. The observable universe, the portion accessible to our instruments given the finite speed of light and the finite age of the cosmos, may simply be too small a sample to contain evidence of intelligence that exists beyond its edge. The universe is almost certainly vastly larger than what we can observe. The silence of our observable bubble is not the silence of the universe. It is the silence of our corner of it. The James Webb Space Telescope, launched at the end of 2021 and fully operational in 2022, has given astronomers the ability to analyze the atmospheric chemistry of exoplanets with precision that was previously unachievable. When a planet passes in front of its parent star, a small fraction of the starlight filters through the outer edge of the planet's atmosphere. Different molecules absorb different wavelengths in characteristic fingerprint patterns. By identifying which wavelengths are missing from that filtered light, researchers can identify specific compounds in an atmosphere from thousands of light-years away. In 2023, researchers using James Webb reported the detection of carbon dioxide and sulfur dioxide in the atmosphere of K218b, a world approximately 2.5 times Earth's size, orbiting in the habitable zone of a cool star roughly 120 light-years distant. Then, in 2025, the same team published results announcing the apparent detection of dimethyl sulfide in the same atmosphere. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton. It has no confirmed pathway for production by non-biological processes at the concentrations the data implied. The signal was described as exceeding the 3 sigma threshold of statistical confidence. The scientific community responded with genuine excitement and appropriate caution in equal measure. The detection has not been invalidated. It has not been confirmed. It is currently the subject of continuing analysis and debate, exactly as the scientific process is supposed to work. What this represents, regardless of how the debate over K218b ultimately resolves, is a proof of concept. Thus, instruments needed to detect biologically significant atmospheric chemistry on distant worlds now exist. Within this decade, researchers expect to have characterized the atmospheres of dozens of habitable zone planets in enough detail to begin building a statistical picture. If multiple independent worlds display atmospheric signatures that depart from purely abiotic chemistry, the case for widespread life will become very difficult to challenge. For the first time in history, the answer to the Fermi Paradox may lie within reach of instruments we have already launched. METI stands for Messaging Extraterrestrial Intelligence. Unlike passive listening programs, METI involves deliberately transmitting powerful targeted signals toward specific stellar systems in hopes of initiating contact. The reasoning is direct. If every civilization in the galaxy is waiting for another to transmit first, nobody ever makes contact. Someone has to go first. The counter-reasoning is equally direct. We do not know who is listening. We do not know their intentions. We do not know their capabilities relative to ours. Revealing our location and current stage of development to an unknown audience carries risks that cannot be measured. Stephen Hawking stated publicly before his death that attempting to contact extraterrestrial civilizations was, in his judgment, dangerous. He drew his analogy from the historical record of contact between technologically unequal civilizations on Earth, where the outcome for the less advanced society was consistently catastrophic. A substantial number of researchers have argued that active messaging should require global consensus before any organization proceeds, given that any response would arrive decades or centuries later and would affect every human being alive at that time. Others argue the reverse. If the dark forest model carries any validity, we are already visible. A century of broadcast radio and television has created an expanding electromagnetic bubble now more than 100 light-years in radius. Any civilization within that distance already knows a technological species exists here. Going quiet now accomplishes nothing. The debate also raises governance questions science is not equipped to resolve. Who has the authority to speak for Earth? No international treaty currently governs METI. Individual observatories and private organizations can, in principle, transmit anything they choose without global consultation. Several high-powered targeted transmissions have already been sent without any broader human consensus. What makes the METI debate more than academic is capability. The capability exists. The will exists in some quarters. What does not exist is any agreed-upon protocol, governance, structure, or consensus. The question of whether to call into the dark knowing nothing about what might answer, or to remain quiet in a universe that may already have noticed us, is among the first, genuinely, civilization-scale decisions humanity faces in the realm of space. There is a version of the Fermi answer requiring no telescope, no radio signal, and no distant destination. It asks only for a careful examination of our own biology. The genetic code is universal. Every known form of life on Earth, every bacterium, every plant, every animal, employs the same fundamental system for translating DNA sequence into protein structure. This universality is explained by common descent. But some researchers have posed a sharper question. Why this particular code among the enormous number of possible alternatives? The specific encoding system used by all life on Earth appears to be highly optimized. Studies have shown it is remarkably resistant to mutation errors compared to what most randomly generated alternative codes would produce. Physicist Paul Davies has written about the possibility of a cosmic legacy. The idea that a sufficiently advanced civilization might encode information into the genome of biological organisms seeded across the galaxy, not as a conventional message, but as an archive meant to persist indefinitely. DNA is extraordinarily information-dense and extraordinarily stable under the right conditions. A message encoded within the non-coding regions of a genome, the roughly 98% of the human genome that does not directly encode proteins, could theoretically survive intact for billions of years. Researchers have begun systematically analyzing genomic datasets for mathematical structures or information-theoretic patterns inconsistent with purely evolutionary origins. No confirmed result has emerged, but the search continues. There is also a simpler version of this idea requiring no encoded message at all. If life on Earth originated elsewhere, whether delivered here intentionally or through natural interstellar transport, then our biology itself constitutes evidence of life's existence somewhere other than here. Every cell in your body may carry the chemical signature of an origin that began on another world. The answer to the Fermi Paradox may have been inside us throughout our entire existence as a species. Not in our instruments, not in our telescopes, in the molecule that defines every living thing we have ever found. We have been scanning the sky for signals. The deepest signal may be the one we are assembled from. Every theory examined here offers a different resolution. Some hold that the universe is filled with life too primitive to send a message. Some hold that civilizations ignite brilliantly and obliterate themselves before reaching out. Some hold that intelligence is so vanishingly rare that we may be the only minds in this corner of reality that have ever formed. Some hold that the silence is curated, or temporal, or a product of perceptual limitations we have not yet overcome. We do not know which of these is correct. That uncertainty is not a failure of science. It is the honest edge of what any civilization at our stage of development can know. But suppose we accept the starkest possibility, that the silence is genuine and permanent, that no other technological civilizations exist in this galaxy, and that the reason is some combination of everything we have examined. Life is rare, complexity is rarer, intelligence is rarer still, and the civilizations that do manage to emerge are brief and isolated, separated by unbridgeable expanses of space and time. If that is true, what does it actually mean? It means, first, that our sense of responsibility must expand to match the scale of the situation. If we are the only minds in this galaxy with the capacity to ask these questions, then our survival is no longer purely a human interest. It becomes a cosmic necessity. The universe has, in us, produced something capable of observing it, describing it, and perhaps eventually transforming parts of it. If we end ourselves, that capacity disappears without a successor. It means, second, that everything we create acquires a different weight. Every advance in knowledge, every scientific discovery, every work of culture and art may be the only instance of something that exists nowhere else. It means, third, that exploration itself is transformed. If the galaxy is largely empty, becoming an interstellar civilization is not the act of joining a community that already exists. It is the act of beginning to build one. Every world we eventually reach, every system we enter and perhaps one day inhabit, we would arrive at as the first mind to ever encounter it. The gravity of that firstness is nearly impossible to hold in the mind all at once. It means, fourth, and perhaps most urgently for this particular moment, that the question of whether we navigate our own critical phase carries enormous weight. Artificial intelligence, engineered biology, climate disruption, and geopolitical instability are all compressing together within a window that, on cosmic timescales, is essentially instantaneous. Whether we navigate it successfully matters enormously if we are alone. It matters even more if our survival might one day answer, for some species millions of years from now, the same question we are asking tonight. Gazing at the same sky, wondering in silence whether they are the only ones. We began tonight with a single question. Where is everyone? We have moved through layer after layer of possible answers and arrived not at a clean resolution but at something more honest. A portrait of a universe that is, in every direction and at every scale, asking something in return. Whether life is abundant or vanishingly rare, whether the filter lies in our past or directly ahead, whether the silence is natural or managed, or simply the product of limits we have not yet overcome. The silence itself carries meaning. It tells us that whatever we are, it is not ordinary. Whatever happened on this world, in this century, in this blink of cosmic time, is not incidental. And whatever follows is not something the universe will determine on its own. That determination falls to us. The universe is vast past anything language can capture, old past anything the mind can truly hold, and as far as we can tell, quiet in every direction we listen. But quiet is not the same as vacant. Vacant is not the same as finished. Every answer we have examined tonight opens onto more questions. Every theory we have traced runs back to the same junction. This civilization, this century, this choice. The silence does not answer itself. It waits for whoever is listening to decide what to do next. And maybe, when you think about it clearly, that waiting is not indifference. Maybe it is the universe's way of asking whether we are ready. The stars have been patient for 13.8 billion years. The next move belongs to us. Consider also how the Drake equation exposes not just where our knowledge runs out, but what the consequences of that ignorance actually are. When a single variable swings by a factor of 1,000,000, it takes the final answer from a galaxy crowded with conversation partners down to a galaxy that has never produced a second conscious thought. We have no other science that operates this way. In physics, we can bound our unknowns with experiments. In chemistry, with reaction rates. In biology, even with a single example, we can reconstruct evolutionary pressures. But with the emergence of intelligence, we have exactly one data point, and it is the one we are standing inside. Every inference we make from it is circular at some level. We built intelligence to study intelligence, and then asked what intelligence requires. The equation does not give us answers. It gives us a map of our own ignorance, and the map is enormous. The question of the great filter connects intimately to how we think about our own trajectory. When researchers in existential risk model the challenges facing civilization this century, they tend to identify certain transitions as particularly dangerous not because they are inevitable catastrophes, but because they represent moments at which the gap between capability and judgment becomes especially wide. The development of nuclear weapons was one such moment. We barely navigated it, and in some respects we have not finished navigating it. The current emergence of artificial systems capable of sophisticated reasoning may be another. Not because the technology is inherently destructive, but because the window in which it can be developed before the wisdom to govern it has accumulated may be narrow, and we may already be inside it. The great filter framing does not tell us whether we will succeed. It tells us that success is not automatic, that the universe provides no guarantee, and that the absence of visible civilizations older than ours is data that deserves to weigh on how urgently we approach the decisions ahead. The rare Earth hypothesis, beyond its specific scientific claims, raises a deeper philosophical challenge. It asks us to examine whether our intuitions about probability in the cosmos are reliable at all. We evolved on a world that was, by any plausible accounting, extraordinarily improbable. Our intuitions about what is normal and what is rare were shaped by our experience of this one anomalous place. When we imagine the distribution of life across the universe, we tend to project Earth-like situations because Earth is the only situation we have ever known. But there is no reason to believe that our particular combination of factors represents a common outcome. It may represent an edge case in the actual distribution, an outlier so far from typical that our strong intuition that life should be everywhere is simply a failure of imagination imposed by the limitations of a single data point. The dark forest logic, if taken seriously, also changes how we interpret the wow signal, Boyajian's star, and fast radio bursts. Under most frameworks, these anomalies are interesting because they might be evidence of alien transmission or alien engineering. Under the dark forest framework, the silence following these anomalies takes on a different character entirely. If any civilization advanced enough to generate detectable signals is also advanced enough to understand the logic of first strike preemption, then signals would be the last thing they would produce. The wow signal may be anomalous precisely because it was an accident, a momentary leak from a civilization that went immediately dark upon realizing its error. Boyajian's star may be anomalous because megastructures, by their nature, are hard to completely hide, and because the civilization that built them may no longer exist to maintain concealment. Fast radio bursts may be the byproduct of engineering so advanced it did not even register the possibility that someone was watching. In each case, the dark forest interpretation does not make the anomaly more explainable. It makes the silence around the anomaly more meaningful. The ocean world's argument points toward something that has implications for how we design future search strategies. If a substantial fraction of potentially inhabited worlds in the galaxy are sealed beneath kilometers of ice, then any survey strategy that relies on detecting electromagnetic transmissions from the surface of those worlds will systematically miss them. The civilizations most likely to exist, by the logic of subsurface ocean habitability, may be the civilizations least likely to ever generate a detectable electromagnetic signature. This means that our search, even if conducted perfectly by our own standards, could pass directly over inhabited world after inhabited world without the slightest indication. The completeness of our silence may not be evidence of the rarity of life. It may be evidence that we have been searching in the one dimension of the problem space where inhabited worlds are least likely to announce themselves, the cognitive, barrier argument has an implication that researchers are only beginning to grapple with seriously. If genuinely alien intelligence could exist in forms our instruments are structurally incapable of recognizing, then the problem of detecting it is not primarily a technology problem. It is an epistemological one. We cannot build a detector for patterns we do not know exist. We cannot write search algorithms for structures we have never conceived. The limitation is not in our hardware. It is in the conceptual vocabulary we bring to the search. Some researchers have proposed that the development of artificial intelligence may offer a partial solution. Artificial neural networks trained on very large datasets sometimes identify patterns in data that human observers consistently miss. Not because the humans are insufficiently attentive, but because the patterns fall outside the categories human perception naturally constructs. If alien intelligence produces signatures that fall outside human perceptual categories, AI systems trained without those same categorical constraints might, in principle, flag them. Whether this approach will yield anything concrete remains entirely unknown. But it represents a genuine methodological shift, a recognition that the bottleneck in the search may be the shape of the searching mind rather than the sensitivity of the searching instrument. The question of what we owe to the future, if we are genuinely among the first minds in the cosmos, is one that conventional ethics has not equipped us to answer. Our ethical frameworks evolved to handle relationships between contemporaries, between beings who share time and space and whose interests can at least in principle be balanced against one another. The idea that our decisions today carry weight not just for our descendants, but for the entire future history of intelligence in the galaxy, introduces a scale of moral responsibility that our intuitions cannot easily absorb. A civilization that destroys itself in this century does not merely fail its own people. If we are among the first, it forecloses possibilities for intelligence that might otherwise have unfolded across billions of years of cosmic history. That is a different kind of moral weight, one that our inherited ethical traditions were not designed to carry. Whether or not we can actually bear that weight, the Fermi Paradox places it squarely before us, whether we choose to think about it or not. And finally, there is what might be called the recursive strangeness of the whole inquiry. We are a species young enough that our oldest written records span only a few thousand years. We are attempting to reason about the behavior of civilizations that may have endured for millions or billions of years. We are using instruments that have existed for decades to search a universe that has been evolving for 13.8 billion years. We are applying a cognitive architecture shaped by the pressures of a small East African environment to questions about the statistical distribution of consciousness across a cosmos containing more stars than there are grains of sand on every beach and desert on Earth combined. The fact that we can even frame the question coherently is itself something close to remarkable. The fact that we cannot yet answer it is not a failure. It is simply an honest accounting of where we stand. We are early in this. We are perhaps the earliest minds anywhere to have asked it. And the asking itself, the stubborn insistence on turning the question over, examining it from every angle, refusing to accept silence as an answer, may be among the most distinctly alive things we have ever done. The self-destruction hypothesis gains additional texture when you examine specific technological inflection points in human history, and ask what would have happened at each of them if the wisdom required to manage the technology had not kept pace, even imperfectly. The development of nuclear weapons in the 1940s was not accompanied by the emergence of international governance structures adequate to the scale of the danger. What followed was 4 decades of near misses, miscommunications, false alarms, and situations in which the continued existence of organized human civilization depended on individual decisions made under enormous pressure by people who were themselves uncertain of the facts. The Cuban Missile Crisis came closer to nuclear exchange than most people alive today understand. Multiple incidents during the Cold War brought strategic arsenals within minutes of launch based on equipment errors or misread data. That we navigated all of them is not evidence that the system was safe. It is evidence that we were lucky, repeatedly, over an extended period. Now, extend that pattern forward. The technologies entering development in this century are in many respects more capable and less well understood than nuclear weapons were in 1945. The governance frameworks being constructed to manage them are, by most expert assessments, less adequate to the challenge than the incomplete frameworks that emerged to manage nuclear risk. The self-destruction hypothesis does not require that civilizations necessarily fail. It requires only that the probability of failure at any given critical transition is high enough that when you compound those probabilities across dozens of civilizations over billions of years, the expected number of survivors rounds to something very small. The simulation hypothesis, while philosophically distinct from other Fermi resolutions, shares something with the rare Earth argument that is easy to miss. Both ask us to take seriously the possibility that the universe, or at least the part of it we can observe, is not representative of what is actually out there. The rare Earth argument says the conditions of our world may be atypical of conditions generally. The simulation argument says the universe we observe may be a rendered subset of a larger reality in which the rules are different, and the apparent emptiness is a feature rather than a genuine property of existence. In both cases, the resolution of the Fermi Paradox requires accepting that our window onto the cosmos is narrower than it appears. This is a genuinely uncomfortable scientific position. Science has historically advanced by treating our observational window as real and building reliable knowledge within it. The suggestion that the window itself is misleading, whether because of selection effects or because of deliberate design, introduces a kind of epistemic vertigo that is hard to stabilize against. But it is important to recognize that discomfort with a hypothesis is not evidence against it. The universe does not owe us an epistemically comfortable answer. There is a version of the first-mover argument that has specific implications for how humanity should think about the next few centuries, quite apart from any question of alien contact. If we are genuinely among the first intelligent species to approach the threshold of interstellar capability, then the decisions we make in this window will establish precedents that later civilizations, if any arise, will either follow, reject, or be shaped by in ways we cannot predict. How we treat other life on Earth as we develop more powerful technologies. Whether we build institutions capable of governing our own technological development responsibly. Whether the civilization that eventually reaches other star systems, if any does so with an orientation toward stewardship or extraction. These are not abstract philosophical questions. They are practical decisions with consequences that may extend far beyond the horizon of any individual human life or any human generation. The Fermi Paradox in this light is not merely a question about where the aliens are. It is a question about what kind of civilization we intend to become, and whether the answer to that question will eventually echo across the galaxy in ways that make the silence of the present comprehensible to whatever minds may come after us. The directed panspermia hypothesis in its most scientifically conservative form, forces us to confront how little we actually know about the conditions under which life first appeared on Earth. Abiogenesis research has advanced considerably in recent decades. Researchers have demonstrated that amino acids, nucleotides, and lipid membranes can form under conditions that plausibly existed on early Earth. They have identified chemical reaction networks that could, in principle, maintain something like metabolism without the full complexity of modern cells. But the gap between these demonstrations and the full self-replicating, error-correcting, membrane-bounded system that constitutes even the simplest known living cell remains substantial. It is possible that this gap will be bridged by future research and that the origin of life will turn out to be chemically straightforward, given the right conditions. It is also possible that it will turn out to require something more. The honest scientific position is that we do not yet know, and that not yet knowing is precisely the opening through which Crick's hypothesis enters. It does not claim to close the question. It claims only that the question is genuinely open in ways that leave room for extraordinary possibilities. The planetary scale of our current civilizational challenge deserves to be stated plainly in the context of everything we have examined tonight. We are the first species on this planet to have built the capacity for self-destruction at the species level. We are also the first species on this planet to have developed the conceptual and technical tools capable of identifying the threat and imagining how it might be avoided. The same cognitive architecture that allowed us to split the atom allowed us to model the consequences of using it. The same institutional capacity that gave us global financial markets gave us international scientific collaboration. The same communications technology that spreads misinformation also enables the kind of collective sense-making that the Fermi Paradox requires. Whether these capacities are adequate to the challenge they have created is the defining question of this century. The universe appears to have run this experiment many times before, and the results, as best we can tell from the data available to us, have not been encouraging. But we are not yet in a position to know whether the experiments before us all failed, or whether the silence simply means we are the first to run it. The closing thought, the one that seems hardest to shake after working through all of this, is not about aliens at all. It is about us. Every single theory we have examined, from the great filter to the zoo hypothesis to the simulation argument to directed panspermia, places humanity at a position of unusual significance. Whether we are the first, the last, the rare, the managed, the seeded, or the simulated, we are not incidental. We are, in every version of this story, the thing the story is about. The question of where everyone else's leads, every time you follow it honestly. Back to a question about what we are and what we intend to do with the extraordinary and precarious situation we find ourselves in. The cosmos is silent. The mathematics says it should not be. And we are, as far as we can determine, the only minds anywhere in this galaxy currently sitting with that contradiction and deciding what it means. That is not a small thing. That may be the most significant thing. The silence around us is not an absence of meaning. It is the sound of meaning waiting to be made. One thread that runs through almost every theory on this list is the question of time. Not in the trivial sense of how long a journey across the galaxy would take, but in the deeper sense of what it means for a mind to exist across timescales that dwarf anything human civilization has experienced. Our oldest institutions are a few thousand years old. Our written history spans less than 10,000 years. Our species has existed for perhaps 300,000 years. In cosmic terms, we are newborns. A civilization that has persisted for 10 million years has existed for more than 30 times the entire span of our species' existence. Its relationship to time, to change, to the long arc of consequences would be so different from ours that we have no meaningful framework for imagining it. When we ask whether such a civilization would contact us, we are implicitly assuming that contact would be a meaningful concept to a mind that has already outlasted 100 human civilizations' worth of history. Perhaps what looks like silence from our vantage point looks like an extremely brief and recent blip from theirs. Perhaps they noticed. Perhaps they are still deciding. Perhaps from inside their experience of time, the deliberation has barely begun. And perhaps that is, in the end, the most honest place to leave the question. Not with a resolution, but with a genuine appreciation of the scale of the unknown. We have built extraordinary instruments. We have developed genuinely powerful theoretical frameworks. We have looked at the sky with more care and sophistication than any previous generation of human beings. And the sky has remained silent. That silence is data. It tells us something real about the universe, even if we are not yet sure what. What it does not do is tell us we are alone with certainty, or that we are watched with certainty, or that the great filter is behind us, or that it waits ahead. It holds all of those possibilities simultaneously, and it will continue to hold them until we either develop the tools to distinguish between them, or we cross some threshold that answers the question in a more definitive and possibly more consequential way. Until then, we are left with the most ancient and most productive of all, human postures in the face of the unknown. We keep looking, we keep thinking, we keep building the instruments that might, one day, finally break the silence. The stars have waited 13.8 billion years for a mind capable of asking why they are quiet. We owe them and ourselves the effort of finding out.